Have you ever just looked up at the night sky and been totally blown away? For most of human history, all we could see were a few planets and a whole bunch of stars. But then, an invention came along that literally gave us a window to the rest of the universe. So today, we're going to dive into how telescopes actually work and how they bring the cosmos right to your doorstep.
All right, let's start with the biggest question of all. You've got light from a galaxy that has been traveling for, say, millions of years. By the time it gets to us, it's just this incredibly faint little speck. So how in the world do we turn that tiny dot of light into a jaw-dropping picture of a spiral galaxy? Well, it's not magic, I promise. It's actually a really clever bit of physics that's all about changing how we look at things.
And the secret sauce is something called angular magnification. It sounds complicated, but check this out. Hold your thumb up close to your eye. It can literally block out a whole building across the street, right? That's because it's taking up a huge angle in your vision. A telescope's whole job is to take something tiny and far away, like a planet, and make it take up a much bigger angle, so it looks way, way closer and more detailed. Now, the very first gadget to really nail this trick was the refracting telescope. Yep, this is the classic one you're probably picturing, a long tube with a big piece of glass at the front. It all works by bending light, or refraction, to create that awesome magnification. Okay, so this diagram shows you everything that's happening inside. It might look a little technical, but trust me, we'll walk right through it. See those parallel lines coming in from the left? Imagine that's light from a super distant star. We're going to follow its path as it goes into the telescope and comes out the other side into our eye.
First up is the most important part, the objective lens. This is the big piece of glass at the very front. Its job is basically to be a giant light bucket, to collect as much light as it possibly can from something really faint. It grabs all those light rays and bends them, focusing them down to create a tiny, real image inside the tube. And, fun fact, that image is actually upside down.
So, you've got this tiny upside-down picture floating in the middle of a dark tube. How do you see it? Well, that's where the eyepiece comes in. The eyepiece is basically a super powerful magnifying glass. It takes that little image from the objective lens, blows it up, and shoots it right into your eyeball so you can see all that amazing detail.
Okay, so we've got these two lenses working together as a team. But how much can they really magnify something? Well, like I said, it's not magic, it's just physics, and it all boils down to a really simple and elegant formula.
And here it is. This is the secret recipe. The magnifying power, which we call m, is just the focal length of the objective lens, that's f sub o, divided by the focal length of the eyepiece, f sub e. It's that simple. So what this tells us is that you want a long focal length for the objective and a really short one for the eyepiece. That's how you get some serious power.
Let's run some numbers to see how this works. Let's say our big objective lens has a focal length of 100 centimeters, and we've got a little eyepiece with a focal length of just 1 centimeter. We just need to plug those two numbers into our formula.
And boom, there you go. 100 divided by 1 is 100. That gives us a magnifying power of 100x. That means whatever you're looking at will appear 100 times larger than it does with just your eyes. That is some serious power from two pieces of glass.
So you might be thinking, awesome. To see farther, let's just build a refracting telescope with a bigger and bigger lens. And, in theory, that's a great idea. But in the real world of engineering, that's where we run into some very, heavy problems.
Yeah, here's the catch. Making a huge, perfect piece of optical glass is next to impossible. For one, they weigh an absolute ton. They are incredibly expensive and difficult to make without any flaws. And get this, a really big lens can actually start to sag under its own weight, which totally distorts the image. On top of all that, lenses can act like tiny prisms, causing a weird rainbow fringe around bright objects. That's called chromatic aberration, and for astronomers, it's a total deal breaker.
So that brings up a really important question. If giant lenses are such a headache, how are we building these absolutely monstrous observatories that can see almost to the edge of the universe? Clearly, we needed a whole new game plan. And that new game plan was brilliant in its simplicity. What if we just got rid of the main lens altogether? Instead of bending light with glass, astronomers figured out they could just bounce it off a perfectly curved mirror. This changed everything. So check out this design. This is a reflecting telescope. The first thing you'll notice is there's no big lens at the front. Instead, the starlight travels all the way down the open tube and hits a huge bowl-shaped mirror at the back. That is our new objective.
Here's the play-by-play. Light comes in, hits that big objective mirror at the base, and gets focused back up the tube. Then, it hits a smaller secondary mirror near the top. That little mirror bounces the light again, this time through a hole in the middle of the big mirror and right into the eyepiece. It's an absolutely genius way to fold a really long light path into a much shorter, more compact tube.
Okay, so let's zoom out. We've seen two totally different ways to build a telescope. You've got team lens, the refractors, and team mirror, the reflectors. Let's put them head to head and see why modern astronomy made a very clear choice.
This table really sums it all up. Refractors use a lens, reflectors use a mirror. Now, refractors are simple and tough, which is great, but they're stuck. You just can't build them big enough because of the weight, cost, and sagging problems. Reflectors, on the other hand, can be built to truly enormous sizes. Why? Because you can support a mirror across its entire back. It's completely stable. And that single massive advantage is why every major research telescope in the world today is a reflector.
So, what are the key things to take away from all this? First, remember that simple magnification formula. It's just the objective's focal length divided by the eyepieces. But even more important is this idea. The real power of a telescope, its ability to see faint, faraway objects, all comes down to the size of its objective. The bigger the mirror, the more light it can gather. And in astronomy, light is everything. It's the data, it's the history, it's the story of the universe. So as we build bigger and bigger mirrors, we're not just building telescopes, we're building time machines. And that just leaves you wondering, what incredible secrets are we going to uncover next?